everyone. I want to go over a bit more about my what was supposed to be a brief introduction to C, but it always ends up being longer than you expect. We're going to go over some of the fundamentals of C, then we're going to look at functions very soon. But first, I want to look at some arithmetic and input and output. Now, the reason I want to look at this is because it directly relates to your assignment, and therefore I want to make sure you get exposed to that early. So we'll do also a little bit of, not live coding because I've already coded it, we'll just see what it looks like. So let's look at arithmetic. Now, as we've said before, when we declare memory, like I say, integer I, for example, I get a bucket or I get a bin to put stuff into. So that bin happens to be 32 bits. An integer is 32 bits or 4 bytes, and that's how much I can put into that space. A character is 1 byte to store, let's say, the character X. Now that is a single character, not multiple characters, not a string of characters. It is a single byte which stores a single character value. We also have things like a short, which is half the size of an integer. So this should be the short should be 16 bits. Long is actually 32 bits, the same as an integer. It used to be twice as long as an integer, but since when integers doubled in size, long stayed the same, just to make it fun. A long is twice as long as a long. It is actually 64 bits. That would be 16 bytes of data. We even had things like floats and doubles, a float being 32 bits and a double being 64 bits of data to store a floating point number. And finally, we had one other data type, basic data type that we were sort of avoiding for right now. It's void. Now, void, actually, you can store stuff in there. It is normally just a chunk, some kind of data is being stored there, but normally it's reserved for I don't want to return something in particular, or I'm not saying what kind of data it is. We see this often with like our main method. When we're not returning something from a function, when we get to functions, when we're not returning something, we'll return void, as in don't return squat, don't return anything. Later on, we'll do strings. So I'm actually going to let me play a little bit more. Actually, I'm going to do a little bit of live coding, but I want to show you all of this in action. So let's take a quick jump over here and our hello world demo. I put a breakpoint down here. I'm going to move that breakpoint, and I'm going to, let's see here, float. My float is equal to 4.3, F because it's a floating point number, and I should also put an L and spell the word float correctly. Double, my double is equal to 4.3, or actually let's say my float, no, let's say 4.3. Notice for double, I don't put the F. For floats, I put the F to say whether it's a float or a double. And then we're going to do something a bit crazy, and then I'm going to say my int is equal to, I'm going to cast it. So we're going to look at casting very soon, and my double. We're going to look at a bunch of different things. So let's make this my long, it's an unsigned int. We don't need it, but I'm going to do it anyways. Okay. When we get later on in the lecture, we are going to see this and this sort of thing. This is what's called casting. I am saying in this particular situation, see this character? It's actually a type of character. No, it's not a character at all. It's actually, these aren't the droids you're looking for. This is actually an unsigned integer. It's not a character at all. So pretend this thing is not a character. Despite it being a character up here, pretend it's not a character. I want you to consider it an unsigned integer. When we talk about signed and unsigned, I think we've already looked at this, but if we haven't, unsigned being it is purely positive numbers. You do not have negative values for it. Signed, or the sort of default, my int, like up here, my int is -2. My positive integer, I'm just going to make it whatever my int is, and we'll see what that result ends up being. All right, so let's pop a breakpoint in here. Let's have a look at what this thing is going to do, and let's actually compile it. So what is this code actually going to do? I'm going to make a character called mychar. Very original names. It's going to be the value C, the character C. That has to be encoded in a computer using zeros and ones. When we get to characters in more detail, we'll see this in action. This is what's called ASCII. It is a standardized approach for representing predominantly English letters of the alphabet using a number. Because we need to be able to store it somehow. So we all agree, yep, capital A is going to be this number. Capital C is going to be this number. The carriage return or a new line is going to be this number. A tab is going to be this number. Anything you could type on an English keyboard, there's a representation here, essentially. And so we have this nice, very limited to English, essentially, way of converting a character to a number so that we can store it in the computer. This was developed in the 1960s, in case you're wondering why it's only English. Unicode is what you use for if you want to represent all the other languages in the world, because way back in the day, there was a limitation on the amount of storage, and then suddenly you go, well, really, maybe, there are billions upon billions of people that don't speak the English language. Maybe we should be representing those people as well. Yeah, it's a good idea to use Unicode whenever you can. Characters is just a shortcut when you're programming, but if you're ever doing user input and output, you always go Unicode. Unicode being this way of representing any language, almost pretty much every language that's spoken on Earth right now, or any written language, I guess, on Earth. So this is, I'm going to get a character C. We're going to see what that value is. We're going to get my integer. It's going to be the value -2. We're going to look at my positive integer. That's going to be the value of whatever my int was. So this new variable is going to be assigned whatever this thing here is. I'm going to make my long, which is going to be this value right here. Heck, what the heck? I'm going to do long my long, I'd say. And so my long. All right. Let's see how big this thing is. Let's also, I'm going to get ahead of myself by a couple weeks. Let's do size of. And my long. And then I'm going to, let's keep that in somewhere. L size. And unsigned. I have a syntax error somewhere. No, I don't. Unsigned int LL size is equal to size of my L long. All right. Let's save this. Let's compile it. All right. So what are we doing? So first of all, I'm going to make an unsigned integer, make it the same value as my int. Let's see what that does. We're going to make a long, which should be twice as long as an integer. Going to make it the exact same value as my int. We're going to make a long, which we're going to make it the same as the long. Let's see what happens there. We're going to also check to see the sizes of those two variables. How big is the box storing my long? How big is the box storing my long? That's what the size of is going to give us. After that, we are going to, I have an unsigned long just because to show I can. I'm going to have an unsigned character value for this character I have. So my character, I'm going to say, no, it's not a character. It's an unsigned integer, and let's see what the value is. We'll see that nothing changes. We're going to have a short, which is half the size of an integer. We're going to also make a float, which is 4.3, a double, which is going to be the value of 4.3, and then we're going to cast that double, which is 4.3, into being an integer, and we'll see something different in that case. Okay, lots to go over, so let's have a look at what we have here. Let's run our code. I have a breakpoint there. I'm going to go one step further just so we can see what our breakpoint looks like. Nope, I just continue my code. Okay, let's actually put my breakpoint here, and we'll go work our way down. Okay, my character is the value C. Great. What's C? Oh, actually, if I go to hexadecimal, actually, I don't even see the hexadecimal display. Let's do a couple more of these steps here. Boop-a-doo. All right, and I'll go past the my long. So, my integer, as a hexadecimal display, this is what I did here. Hexadecimal value. I could see what this value is. It's a bunch of F's and an E. Why? Because we did 2's complement. Remember that when we flipped all the bits and added 1, right? That is what -2 is as a 2's complement number. In case you wondered what we were doing there, Sometimes you actually need that because you will actually get the raw binary and not know what the heck it's doing. So, for example, if I have my char, I could put a breakpoint there. Let's do one more attempt at this. I want to see what my char looks like before we initialize something. Okay, my char, nothing's been initialized, and the value for my char is something ridiculous. And you'll say, what the heck is this? Is negative 52 or this, whatever this the heck this character is, and you go, what's going on? And if you look at hexadecimal, it's actually 0xcc. So the hexadecimal value for that is cc. I know, because I've been doing this for a while, I know that any uninitialized variable, in debug mode at least, if you didn't set a value to it, it's going to get a bunch of C's in a row. That's the way I know, slap in the face way I know that this thing has not been initialized yet. That's how you can tell. So in case you get a bunch of C's, you go, hey, I didn't set my value yet. Let's go one step. Okay, now it's a normal value. It's the value 63, the numeric value 63. My int is going to be the numeric value -2. As a hexadecimal number, it's a bunch of F's, F, 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 E. Right? If I convert this back to get rid of the hexadecimal display, hey, there it is, -2. The value C is the value 99. I'm going to get my pos int. It hasn't been initialized yet. How do I know it's not been initialized yet? Because it's a bunch of C's here, right? I go one step further, and I'll see what the value is. All right, it's FFFFFE. The same thing as my int. Notice nothing has changed between the unsigned int and the signed int, except, so under the hood, it's the same binary number. But notice what happens if I actually show the number. It is a huge positive integer. This is a really small negative value, and if I say it's an unsigned integer, it's a huge positive value. The same binary number, how you interpret it is radically different. I don't know how many people speak French and Spanish, but I think it's gâteau, yes, gâteau, where it's cat in Spanish and it's a cake in French, right? What? There's lots of cases. It's how you interpret it. The same sound is being made in both languages. They mean radically different things. In this case, the binary number is the same in both cases, but one of them is being treated as a positive number, and it's a huge number, and this is considered a negative number, and it's a very, relatively, the magnitude of that negative value is really small. It's -2. Let's look at what my long does. Right now, it is a big crazy number. Why? Let's have a look at it again, and hexadecimal display. My long, oh wait, it's not initialized. Bunch of C's. All right, let's go one step further. Let's see what we get. Hey, it's a whole bunch of F's and an E. It does this, it uses what my int has, and I just stuffed a bunch of F's at the front. It's doing what you expect. It is going to be the value, and I'll convert it back again. It's the value -2. How about my long? Let's have a look at the length of my long. Oh, it's also -2. And if I look at the size of the hexadecimal number, it is the exact same length as my int. Same number of bytes between the two of them. They are both, there should be 8 bytes in there in total. Okay, and that's how many hexadecimal values I have, right? There should be 8 of them in here. Let's do one more. L size is some uninitialized value. Let's do the next 2 steps. So one more step, 4, one more step, and so this number of bytes this thing is for my long is 8. Is 8. Oh, that's weird. I'll have to look at this a bit more. So we'll notice that the long is twice the size of the long, but I am getting 4 bytes. Yeah, sorry. Yes. Each hexadecimal number is you represent using 4 bits. 8 bits make a byte, so I will have 8 hexadecimal numbers, but 4 bytes to represent it. 4 bytes times 8, 4 times 8, 32 bits. Okay, my math was slightly wrong in the previous example. It is 8 bits make a byte, so I have 4 bytes of data, which each byte can be represented using two hexadecimal values for a grand total of 8. So a long is 8 times 4, 8 times 8, 64 bits, and a long, just a long, is the same size as an integer, which is 32. Okay, let's go a bit further. Let's do an unsigned long. So what does that look like? This is going to be a ridiculously large number, at least I hope. Remember, I'm taking my int, which is a bunch of f's and then an e. I'm saying, no, I make it twice the size, but it's still going to fill in the same way. It's going to be a bunch of f's and an e at the end, but as a positive number, it is a ridiculously large positive number. Here is, I'm going to take my char, which is the value c. I'm going to say, no, it's an integer, and char val, I could predict ahead, it's going to be equal to 99. It is the value, ASCII value for c. So char val here, that should be 99 when I'm done. Let's go one step. Let's see it in action. Hey, there it is. Char val is equal to 99 right here. How about this short? A short is half the size of an integer. So instead of 4 bytes of data, it should be 2 bytes of data, 16 bits. So let's have a look at it. So I'm going to take my int. It's going to be, hopefully it should still be -2, but only using 16 bits. So let's have a look. And so the value for my short is actually -2, same as my int. But if we look at the hexadecimal value for it, we'll see something. Where is it now? It's in here. Here's my short. 4 hex values to represent it. That's 2 bytes, 4 hex values. So it works. Here is a float. So it's 4.3. It's going to be, notice it's not even letting me see just the raw hex value, I don't think, in this thing here, right? Because it's not going to be useful at all for you to read. It's 4.3. Notice it's not actually just 4.3. It's 4.3, a whole bunch of zeros, and a 1.9. Why? Because you can't properly exactly represent floating point numbers using a computer. You don't really represent pi with math just as the right value. It's an irrational number, therefore that you can't exactly represent it. You get close enough. So this is our close enough value, but it means that when we're trying to match things like, is this thing equal to this, your math can get a little wonky. That's another key reason why we don't use floats and doubles unless we need to. If I'm just counting up by 1, I'm using an int. I'm not using a double. I'm not using a float because I need to make sure that the number is exactly the number I'm looking for. And the math is just faster and easier. So unless you need it, don't use floats and doubles unless you need like a floating point number. Here's my double. Let's have a look at this one. It should be, it's going to be twice the length technically, but you may not be able to see it. 4.3. Oh, look, it rounded down in this case, right? 4.299999998. It's essentially 4.3. It's close enough, but it's not exactly right because you cannot properly represent these numbers on the system, right? There's a limited amount of precision that you can have with floating point numbers. One of the little quirks of computer science. Now, let's have a look at this. This actually might screw up something here. 4.3, no, it'll work out fine. So my double is going to be this number here. Let's look at what do we predict this number to be. And in fact, I might run this whole thing again just so I can see this with a different value. So I would expect it to round down to 4. Great. It's going to be 4. My int should be the value 4. Hexadecimal value 4. Let's go to just a straight up display. There he goes, 4. I'm going to run this again. But instead of 4.3, I'm going to say 4.9. Or let's say 4.8. Right? If I round, now I would round up, right? Except I'm not going to. So let's run this again. Let's look at it again. And I'm going to get rid of this breakpoint because there's no need for it. Oh, I put it back in. Get rid of this breakpoint. Continue. And I'm going to go down one more step and see what my value is. Oh, it's 4. That is the other little gotcha along the way. Casting from a double to an integer truncates. It does not round, it floors. It takes 4.89237 or whatever number you give me, whatever the number is, and just says 4. Chop off the rest. That is a huge change for what you would expect for a lot of people. People expect rounding up, rounding down, but it's consistent. If I have 4 point whatever, it's 4. If I have 5 point whatever, it's 5. And I have a truncation. I can convert between integers and floating point numbers relatively easy. I also have remainders and the like. But if you assume just normal rounding, it will not work for you. By the way, if you want to figure this out, let's do this. My remainder is equal to, what could I do here? Oh, so let's do my, what's this going to do? This is going to give me, because I have a double here and an integer here, I'm going to do double arithmetic. This is going to give me a double as a result. And then I'm going to need to cast it back down to whatever it was before. So I'm going to say it's an integer. No, it's actually an integer. And this should give me whatever the remainder was. And I took the original, so this is going to cast down. Actually, that's not going to work. That's not what I'm looking for. I want something like, I'm trying to think of a good example here. Because what I really want is whatever, that's what I'll do. So my double minus my int, and this would, for positive numbers at least, give me whatever is left over. So if my double is 4.8, this will be 0.8 afterwards. My remainder will be 0.8. So we could do something like that, for example. In case you want to know how we would do division with integers, we could do things like this. So int, actually we'll look at this in a second, but let's just run one example. My rem2, which is equal to, let's say 14, and then I'm going to do 3, and my div, I'm just getting ahead of myself here. So what the heck are those two doing? What would we expect? Let's compile it and let's see what happens. Again, if you don't know, throw it at the compiler, see what happens. Half the time I don't remember what things do. Throw it at the compiler, see what happens. I do normally remember what things do. I know what this is going to do. But sometimes the ultimate arbiter of what your program does is the compiler. Throw it at the compiler, see what happens, see what the values are. So let's have a look at this. So my int, it's going to be 4.8, it'll be round down to 4. That's what I expect. 4. If I want to get whatever remainder is, my remainder, it's going to be 4.8 minus 4 now. So that should give me 0.8. And if it does, 0.7999, 0.8 essentially. I'm going to do integer arithmetic in this case, or integer division. So 14 remainder 3. So this is, if I divide 14 by 3, what is left over? So 14 divided by 3 gives me a grand total of, so 12 is equal to 4 times 3. Okay, so 4. And then there's a remainder of 2. Let's have a look at this, because maybe I'm wrong. I actually was wrong in one of my lectures. No, it gives me a remainder of 2. And 14 divided by 3, as whole numbers go, the only thing I can do is 4 times 3 is 12, and there's some remainder. So 14 divided by 3 should give me 4. 4 times 3 is equal to 12. The closest number below 14 that is a multiple of 3. So 4 is my value here. And by doing that, I can regenerate the 14. It's the remainder plus 3 times 4. 3 times 4. So 12 plus 2, that'll give me 14. I can still do the same basic math, but just be acutely aware of when I'm doing, let's say, division, it will truncate. It will not give me 4 point something. It will give me 4 because I'm dealing with integers. I'm dealing with only whole numbers, And there's no such thing as 4.3 or 4.29497. There's just 4. I only get a whole number as a result. Integer arithmetic is different than floating point arithmetic. It was the same in mathematics, you just may not have realized it. If I had two integers and I, divide an integer by an integer and I say you can only have integers, you get an integer. You don't get a floating point number. It is what we had in mathematics, you just may not have realized it. Okay, so this, we have casting here. We've dealt with different sizes of how big the variables we're storing. We looked at characters a little bit. We even looked at the size of function, which we weren't going to get to till later in the term. That allows me to figure out how big a long is, or how big a long is. I just call size of in front of it. All right. So where are we now? Here we go. And here we go. So we are not going to deal with strings quite yet. We will get to strings very soon. In fact, we'll look a little bit at strings the very next lecture when we look at printf statements. But we're not going to look at how they're actually stored yet. It's actually a whole thing. It's a lot more convoluted than it might seem. Or we could just pretend there's some magic involved, but I didn't want to use magic. So we'll look at it when we start dealing with arrays. Again, if I have an example, if I have 45 and 72, if I add the two together, I will get 117, and I'm storing these into particular bins. Those bins are just hexadecimal values, or binary values, storing all of this. And the math is going to be the same no matter what. It's how you interpret the number, how you interpret that binary number that changes things. Okay. Just also to give you some examples of C operators, we do have assignment, which is a single equals. Double equals is not the same as assignment. We have to figure out, every language needs to figure this out. C does it this way. Every language needs the interpretation between an assignment and a comparison. Double equals is our comparison. Is 4 equal to 3? Is x equal to 3, for example, in this case here, right? I need to figure out if x is equal to 3. Single equal says make x equal to 3. That is a very different thing. Okay. We have our normal math operators. We have plus, that's plus sign, minus, we have division, and the asterisk here is multiplication. You've seen it sometimes in your math class. I hope you would have seen it sometimes used as a math operator in math classes. We need something we can just type in. And just putting two variables together doesn't work because you don't know what you're trying to get at there. Our multiplication, the only way to do multiplication, asterisk. We can't use the letter x. We might have the letter x as a variable, right? So we need some symbol. The symbol we're using in C, C++, Java, Python, and every other imperative language I can think of is this thing here, this asterisk, the star, right? Because it's the only thing we can guarantee it looks like math. It looks like multiplication. So again, this is an assignment. This is a check for equality when we do conditionals like, is this greater than this? Is this equal to this? Is x equal to 3? That's when we use this double equals. By the way, in case you're wondering, we have other things we can do. We have, this is not equals. Let's just put the whole words in there. Not equal, right? This is the same as, and this is just a not. This is the same as saying x is equal to 3, not that. If you are old like me and you remember Wayne's World, it is that bad joke that they would tell. They would say something and then put the word not at the end, right? Is x equal to 3? Not that. So x is not equal to 3. This would be only true if x is not equal to 3, or I could have just said x is not equal to 3. Let's put it like that. We have the greater than symbol. We have the greater than or equal to symbol. We have a less than or equal, but it is not this thing. It's this thing here, not this thing over here. So x is greater than or equal to 4. This is the correct way of doing it. X is, I can't do it this way. This is actually looks like it implies. It looks like the x is going over to the 4. It looks like an arrow. I don't write my math that way. So I will have Y is less than or equal to 4. That is doable, but I can't, it's not the other way around. So y is equal, not that either, right? It's always my greater than or equal sign, then my equality afterwards, if I have an equality. We have some other weird little shortcuts along the way. These are not as important yet, but you'll see them later. This is take I, add value 1 to I, and make I equal to I plus 1. This is I is equal to I plus 1. I plus plus is the exact same thing as this. It is I plus, I is equal to I plus 1. It's the same thing here. I could also do plus plus I. There is actually a difference between the two, and it drives me a little bonkers. I plus plus and plus plus I is, do you do the addition first, or do you increase I first, or do you increase I second? That's what, and you get these weird edge cases when you have to worry about the order of these things being done. My suggestion is, if you have to worry about the difference between this and this, don't make your code so complex, because that's when you get into that weird, like, oh, what order is it being done in? You're in a bad position for other people reading your code. So I plus 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 I, we're going to consider them, at least for now, the same thing. It takes I and increases it. We do this so often, that's why we have a shortcut for it. It's just over and over again. We need to take I, increase it by 1. Well, we have that option. Heck, we even have, I forgot to put on the here, but I minus minus, or minus minus I. Both also exist. We have multiplies equal. So I, that is the exact same thing as I is equal to I times 4. Right? You're all these different variants on it. The plus plus doesn't work with multiplies, but the other ones do. Multiplies equals, divide equals, they all work. Remainder equals. Notice we have a series of operations. Here's my arithmetic operation. Here they are in action. Normally for an algebra, we'd have just BM put together. In our case, for a C expression, we need to put that asterisk in there. Division will look like this. We can't go on top of the other one. We can't do x over y. We can't put that. We can't type that easily. So x slash y. If I need remainder, instead of mod, I just put a percentage sign. It's the exact same thing as remainder or mod if you've done that in high school math. We also have an order of evaluations, and that order is exactly the same as in math class. If you did call it bed mass or whatever, it was called bed mass when I was in junior high school. It is, but I think it's anyways, parentheses, parentheses first, multiplication and division second, in order left to right. Then we do remainder, also part of that, left to right. Then we do addition and subtraction after that. Yes, because it would also be exponents in there, but exponents are not part of this. So because we have this order of operations, and so 14 divided by 4 gives me 3. 3 times 4 is 12. There's 2 remainder. So 14 mod 4 is equal to 2. And by the way, I had this wrong. I had a typo in there, and a student picked it out. So in case you thought students pointing out mistakes were not, were there are other keeners, or that professors didn't appreciate it, or we would call you stupid or something, this was very much appreciated. If you see anything at all wrong in the slides, ask, because the worst case scenario for you is that you learn something, because I explain things a different way to make sure you understand it. Base case scenario is I look like an ass and I fix it so everyone else is not confused. So if you see something wrong, ask about it, or you think it might be wrong, or you don't understand something, ask, because I might either explain it better, or you found a mistake and I should fix it anyways. So please, if you find anything like typos, arithmetic errors, ask away. I'm more than happy to get any kind of feedback. It doesn't happen all that often, thankfully, but every once in a while. Basic arithmetic is not my strong point. Okay. In case you're wondering, let's take this random thing. I'm leaving up the whole mathematical operation. But if we had 2 times 5 times 5 plus 3 times 5 plus 7. In math class, what would you have done? You would have done 2 times 5 times 5 as a group, 3 times 5 is a group, and then you would have added this and this and this. So implicitly, you have essentially, oh, I can't really do it. There you go. Implicitly, you have that, right? That is the order of operations because multiplication comes first. I am famous for putting in too many parentheses. I don't think that's necessarily a problem. If you want to, go for it. Put extra parentheses in there just to make sure you understand. If you're having trouble following the order of operations, go for it. So what's it going to do? I'm going to erase this, by the way, just because I don't need it right now. The first thing is I'm going to hit the multiplication first. So the very first multiplication is this one right here. That's what I'm going to do first. I'm going to resolve that. It's going to be equal to 10. So I put a 10 here. This is actually all being done under the hood, but this is actually what C will actually do. It'll be 10 times 5 plus 3 times 5 plus 7. 10 times 5, 50. That's the next multiplies in order. So 50 plus 3 times 5 plus 7. Next thing, next multiplication, this one right here. 3 times 5, 15. So it's 50 plus 15 plus 7. And now I'm doing now there's no more multiplications anymore. I'm on to addition and subtraction. 50 plus 15, 65, plus 7. 65 plus 7 is 72. Boom, y is equal to the value 72. But it's going to be done in a very particular order. There's no ambiguity here. It follows the order of operations for normal math expressions, for normal algebraic math expressions. Okay, so with that, when we come back next time around, we're going to be looking at printf statements, scanf statements, and we're going to hopefully finish up what we're doing for the general tour of C, and then we're going to dive into functions. So we will go into more detail on a lot of these things after this next part, but I want to make sure you're feeling comfortable for the assignment. Okay, so with that, I'll talk to you guys later. Thanks.